Very good afternoon, dear students. So today we are going to continue with our transient response analysis in RLC circuit. In the last class, we had talked about source-free response for your parallel RLC circuit. We had seen the overdamped condition and underdamped condition. So I'll hurriedly recap what we did in the previous class so that you are able to correlate with today's class, and then we will move further. So I'll be very fast in revising the things. So what we had seen parallel RLC circuit. So we had applied KCL to that node. We had developed a second order homogeneous linear differential equation, and we obtained its desired natural response. So the solution of that second order equation was assumed to be V equal to A e raised power st. Okay. Then by substituting this assumed solution, we had obtained this equation, which included the characteristic or auxiliary equation. This was a quadratic equation which had two roots. One is S1 and S2. So these were the two roots, general roots for this quadratic equation. So we had represented those two roots with S1 and S2. By assuming linearity, we had proposed the solution of that second order linear differential equation equal to Vt equal to A1 e raised power S1t plus A2 e raised power S2t. Then we had represented 1 by 2 Rc equal to alpha and 1 by under root Lc is equal to omega naught. And we had designated alpha as exponential damping coefficient and omega naught as the resonant frequency. So once we do that, the form of S1 and S2 was like this, as we are observing on the screen. So then we had categorized our RLC circuit under three conditions. One was overdamped, another was critically damped, and third was underdamped. Overdamped was when alpha is greater than omega naught. When alpha is less than omega naught, it is underdamped. When alpha equal to omega naught, it is known as critically damped. So we have already seen the conditions of overdamped and your underdamped. Then this was the form of overdamped response. Okay, so as I told you, in case of overdamped condition, your alpha is greater than omega naught. You can see that we had seen one numerical example for that. And if you remember, in case of RL and RC circuit, we took into account only one initial condition, whereas in case of this, we had to consider two initial condition. Okay, and this was the general form of your overdamped case. So this was numerical example that we had solved in the previous class. Then regarding form of underdamped response, we have already seen that alpha will be less than omega naught, and the general form of our solution will be like this. That is e raised by minus alpha t common a1 e raised by j omega dt plus a2 e raised by minus j omega dt. And this was reduced to this one. So you can memorize this expression for the case of underdamped response. And omega d was your damping frequency, which was equal to omega naught square minus alpha square. So this expression you have to memorize. So this is the numerical example that we had seen regarding underdamped response. And this is how we had determined the two constants by assuming two initial conditions in the same way as we had done in the overdamped case. So with this background, dear students, now let us move forward. We have seen underdamped response, we have seen overdamped response, and today, firstly, we will look into critically damped response. So this is the case of your critically damped response, and we have already seen that in case of critical damping, your alpha is equal to omega naught. And this we have already seen, that is your alpha is equal greater than omega naught. Okay, so if you substitute the value of alpha, that is equal to 1 by 2 RC, and omega naught is equal to 1 by under root LC, you come to this particular equation. Okay, as I told you in the previous class also, these underdamped overdamped and critically damped response depends on the value of the circuit component. You can see L is there, C is there, and your R is there. These values will decide whether your circuit will behave in critically damped fashion or overdamped fashion or your underdamped fashion. Okay. So for critically damping, the situation is very clear. We have alpha equal to omega naught. In that case, this LC will be equal to 4R square C square. Fine. So LC is equal to 4R square C square. We get L is equal to 4R square C. So if this condition is met, our circuit will behave in a critically damped fashion. Remember this thing. And dear students, this equation which I have shown with a question mark, this equation was for the case of your overdamped and underdamped condition, but this equation will not apply to critically damped. Critically damped case is a bit different in a way that the solution of the differential equation will not be same. So in case of critically damped case, your equation will come out to be like this: second order linear differential equation, d2v by dt square plus 2 alpha dv by dt plus alpha square into v equal to 0. And you all have studied differential equation during your B.Tech first year as well as your +1 +2. So if you solve this equation, your solution will come out to be this one, that is e raised by minus alpha t. In the bracket we have a1 into t plus a2, and where a1 and a2 are the two constants which we have to determine. Okay, so this is the third form of equation which exists for the case of critically damped. Dear students, please remember this thing, that you have to memorize the form of the equation that we will come across while dealing with RLC circuit, and you can directly apply those equations when you solve any numerical related to that. So you must have noticed this point at the bottom of this slide, that is, this critically damped condition is impossible to achieve in practice. So dear students, let me clarify. We have firstly discussed overdamped and underdamped condition. Okay, why are we discussing critically damped condition at the end? The reason is this critically damped condition is almost impossible to achieve in a circuit. Almost impossible. So very rarely it will happen that your circuit behaves in a critically damped condition. So in fact, what is the reason behind that? The reason is that we cannot have the circuit component values which will give us alpha equal to omega naught, or we cannot have so much precision in the component values that your L becomes exactly equal to 4R square C. Definitely there will be some mismatch in the values that we come across related to the circuit components. So since this condition cannot be achieved, so practically we say that this condition is impossible to achieve in practice. So this was with regard to your critically damped case. So, okay, dear students, after discussing this critically damped response, let us move forward. So we have talked about three kinds of responses. One is your underdamped response, another is your critically damped response, and third is your overdamped response. So students, we need to look into that what actually is the meaning of this underdamped, critically damped, and overdamped. I told you in the initial classes also that the meaning of, or these RLC circuits, they are used for oscillations. So if we suppress oscillations, then damping condition arises. So you can see here that if we have underdamped condition, I have graphically represented all these three responses. So in case of underdamped, the amplitude of your oscillation is maximum. In case of critically damped, it is in between. And in case of overdamped, the amplitude of your oscillation is minimum. So students, by changing the values of circuit component, you can decide the amplitude of your oscillations. You can see here in the graph that by changing the value of resistances, you are able to change the damping condition of your circuit. Okay, so it is also written here that your damping can be changed by increasing the size of parallel resistance. So if you increase the resistance, your damping is changed. Say if you move from 6 ohm to 8 ohm, you have moved from overdamped to critically damped. Then from 8 ohm to 10.5 ohm, you have moved to underdamped. Okay, and your response will become oscillatory. Oscillatory means your signal will move from on both sides of your axis when you have under damping condition. So your oscillations will be present during your under damping condition. And obviously your settling time, it is also dependent on your damping condition. So you have to memorize these three conditions of damping, that is your over damped, critically damped, and your under damped. Fine. So till now we were talking about parallel RLC circuit. So students, now we also need to look into series RLC circuit. Okay, so you can see in this figure that your R, L and C, they are in series. Okay, so in fact we do not need any further discussion in series RLC circuit. Whatever analysis we have talked about related to our parallel RLC circuit, that analysis will apply to series RLC circuit as well. We have already talked about that your series and parallel RLC circuit, they are a dual of each other. Okay, so whatever discussion we did in RLC, parallel RLC circuit, that was with respect to voltage. Whereas in case of series RLC circuit, it voltage will be replaced by current. So you can see here that in case of your series RLC circuit, voltage response becomes current response. So this is the equation that we had developed for your parallel RLC circuit, and this is the equation that will be there for your series RLC circuit. So if you apply KVL here, you can see here that voltage across this is LdI by dt. Then we move to resistance, V equal to IR, and then this is the voltage across the capacitor. Whereas this voltage is dependent on the defining equation, and we see T0 defines the initial voltage present across this capacitor. So then what we had done, we had differentiated this parallel RLC equation, and we got this in the similar fashion. We are doing the differentiation again for our KVL equation, and we get this equation in case of your series RLC circuit. So for series RLC circuit, our equation will be L d2I by dt square plus RdI by dt plus 1 by C into I equals to 0. So students, you can compare this equation with the equivalent equation in case of your parallel RLC circuit. You can see that they are pretty much similar. Both are having the same kind of differential equation. Only difference is the constants or the coefficients of this equation. So that means the same kind of analysis that we have developed for parallel RLC circuit, the same analysis will apply to series RLC circuit also. But there will be only one difference. One difference we have seen, that your voltage will be replaced by current, and another thing will be, we have seen the value of alpha and omega naught. So in case of your series RLC circuit, the value of alpha and omega naught will change. Now let us see that. This is your summary of source free series and parallel RLC circuit. You can see here the conditions of overdamped, critically damped and underdamped, they are exactly same whether your circuit is parallel or your series. Okay, now where is the difference? The value of omega naught is also same, that is 1 by under root LC. The only difference lies in the value of alpha. For case of parallel circuits, the value of alpha is 1 by 2 RC in all the three conditions. Whereas in case of series circuits, series RLC circuit, the value of alpha is R by 2L in all the three cases. So you have to simply memorize this thing, that if your circuit is source free series RLC circuit, all that you have to do is you have to calculate alpha differently. In case of parallel RLC circuit, it will be 1 by 2 RC, and in case of series RLC circuit, it will be R by 2L. Okay, rest of the things are exactly same. These are the response equations that we have already seen. In case of overdamped, it will be A1 into e raised power S1t plus A2 e raised power S2t. Then in case of underdamped condition, this we have seen e raised by minus alpha t into b1 cos omega dt plus b2 sin omega dt. And this we just saw 2 slides back, that in case of critically damped condition, your response is e raised by minus alpha t times a1 t plus a2. Okay, so this is all about your series RLC circuit and parallel RLC circuit for the case of source free. In both the cases, we have not assumed any independent voltage source or current source present in the circuit. We have seen the natural response of this circuit. And dear students, now we need not consider the force response separately. The concept of force response we have already seen in case of RC and RL circuit. So if we want complete response, we have to simply add the natural response with the force response. And the concepts of calculating force response in case of inductor and capacitor, we have already seen. So same condition will apply here. So this is the natural response for all the cases. Force response we will calculate by using the concepts we have developed, and in order to obtain the complete response, we will add the two together. Okay. So after discussing the graphical representation, we have seen the source free series RLC circuit. Then we have seen the summary of series and parallel RLC circuit. So now this is the conclusion of this chapter, you can say, that how to obtain the complete response of RLC circuit. This is applicable to both series as well as parallel. We'll discuss step by step what you need to do in order to obtain the complete response of RLC circuit. This is going to be very, very helpful in solving numerical for you people. Okay. And let me tell you, this procedure is same that we have seen for RL and RC circuit. I'm not going to tell you anything new, but just to recap what we have discussed, let me again reiterate those points. So first step that we have to do is we have to determine whether our given circuit is parallel RLC circuit or series RLC circuit. Okay. So first we have to decide by looking at the circuit whether it is parallel or series RLC circuit. And then after doing that, we'll have to calculate alpha and omega naught. We have seen in the summary sheet that alpha is equal to just let me tell you. Yeah, alpha is equal to R by 2L for series circuit and alpha is equal to 1 by 2 RC for parallel circuit. Whereas omega naught is same for all the cases. Okay. So once you decide it is series or parallel, alpha will be calculated accordingly and omega naught will be same for both the cases. So after determining alpha and omega naught, the next step will be to write an equation for natural response. We have seen three conditions: overdamped, underdamped, and critically damped, and we have also seen the corresponding expression for that. So whether our circuit is overdamped or underdamped or critically damped, accordingly we will write the equation for natural response. And these conditions will be determined by comparing the value of alpha and omega naught. After we do that, we will obtain the force response by assuming the steady state conditions for your inductor and capacitor. We have seen that under steady state, your capacitor behaves like an open circuit and inductor behaves like a short circuit. So by doing that, we will be able to obtain force response. After doing that, we'll add force response and natural response, and that will give us the complete response. And students, as I told you in the previous numerical examples also, that in case of RLC circuit, we will have to determine two initial conditions, because in the equations of natural response, we had two variables. So for solving those two variables, we need two initial conditions. One initial condition will be directly determined by either calculating V0 or I0, and another condition will be through derivative of that, that is either di by dt or dv by dt. So by using those conditions, we will determine the unknown constants by applying those two initial conditions. Okay. So before I move further, let me pause for the questions if you have any. Okay, students. Now we need to look into one numerical example. So this is the numerical example that will give us complete response of RLC circuit. So this is the question which is shown on the left hand side. We have two independent sources. One is 4 UT and another is 5 ampere. So 4 UT means this current source is being applied at t greater than 0, means UT is a unit step. So for t less than 0, this current source is not present. So for t less than 0 only this thing is present. So it means initial conditions will be determined with the help of this thing only. We will see to that just few minutes later. Okay. So dear students, as I told you, first we need to look into whether our circuit is series RLC circuit or parallel RLC circuit. So just ignore the sources which are present. You open circuit, current source, this current source also, you can see that this RLC, they are series RLC circuit. Okay. So since we have obtained series RLC circuit, next step is to find out the value of alpha, okay, and the value of omega naught. So we already know the value of alpha for series RLC circuit, that is R is equal to alpha is equal to R by 2L. Okay. So if we calculate, the alpha will come out to be 5, and we know that omega naught is equal to 1 by under root LC. If you calculate the value of omega naught using L and C here, that value will come out to be 3. Okay. And now you compare alpha and omega naught. Since your alpha is greater than omega naught, so what does it mean? That our circuit is overdamped. So let me represent that overdamped with OD. So our circuit is here now overdamped. So since our circuit is overdamped, so the form of our natural response will be this one. That is Vt equal to A1 e raised power S1t plus A2 e raised power S2t. This will be the form of our natural response. Okay. And S1 and S2 are the two roots. So which will be determined by putting the value of alpha and omega naught in this equation. So once we do that, the value of S1 will come out to be -9. -9 will be obtained. And S2 will be obtained as -1. So these are the two roots. So S1 and S2. Fine. So see, this is the natural response equation. We have substituted the value of S1 and S2. So we got the equation A e raised power -t plus B e raised power -9t. This is our natural response equation. Fine. Now we need to determine, next step is we need to determine the force response. So dear students, force response means our circuit in steady state conditions, that is at t equal to infinity. So at t equal to infinity, we know that both these two sources are present in the circuit. At t equal to infinity, this will be short circuit. This will be short circuit. Okay. You can say that it is combined like this. At t equal to infinity, this capacitor will be open circuit. Okay. So if we do that, you see here what is happening. When this is shorted, this current source, this will also be shorted, means this entire current of this current source will move through this short. There will be no contribution of this current source in the circuit. Okay. So means only this 5 ampere current will be flowing through this circuit, through this resistance. So that means the voltage that we will come across this VR will be, current is 5 ampere, resistance is 30 ohm, that is 150 volt. So your VR will be 150 volt. In fact, if you look at the sign convention that we have used here, if you take that, then VR will be -150 volt. Okay. And if you apply KVL, then this VR is nothing but it is equal to VC. So your VC will also come out to be 150 volt. So your force response, that is voltage across the capacitor at t equal to infinity, will come out to be 150 volt. Okay, so your complete response becomes 150 plus a e raised to power minus t plus b e raised to power minus 9t. So this is, you can say, that part one of our circuit that we have just seen. So dear students, after determining complete response, then we need to find out the value of A and B. So as I told you that in order to find out the value of A and B, we need initial conditions. So since here we have to determine the value of voltage across the capacitor, so we need to find out initial conditions across capacitor. So we need to find out VC 0 plus, that is one initial condition, and second initial condition will be dVc by dt at t equal to 0 plus. This is the second condition, as I told you in the basic steps. So in the above equation, in this equation, if you apply this t equal to 0 plus, you will come across 150 plus a plus b, and we need to now find out how come this VC 0 plus is 150 volt. We need to see that. Okay, and how did we come to this thing? I leave this thing to you for the time being today, that you have to find out that how is this VC 0 plus equal to 150. And let me tell you, since this is capacitor, so this VC 0 plus will be equal to VC 0 minus. So first you find out VC 0 minus. So this VC 0 minus will be equal to 150, and that's why this equation has come. So 150 will cancel and a plus b will come out to be 0. Now, in order to apply this second condition, we need to differentiate our complete response equation. So if we differentiate, this is what we get. Now, if you put t equal to 0, we will have minus a minus 9b, and we need to determine that the value of dVc by dt at t equal to 0 plus is 108. So in the same way, you have to calculate 108 value for dVc by dt. And dear students, as I told you previously also, that dVc by dt will be equal to IC. You know IC is equal to C dV by dt. So dVc by dt will be equal to IC upon C. And since this is T0 plus, it will be IC 0 plus. So you need to find out IC 0 plus divided by C, and you will come across this 108 value. So this is also a homework for you people. You have to find out VC 0 plus equal to 150, and then dVc by dt at t equal to 0 plus equal to 108. So if you put all these conditions, you get the values of A and B as A equal to 13.5 and B equal to minus 13.5. So by substituting these values, your final answer will be this one. Okay, so I hope all the things are very clear to you, and this homework which I have given you to determine the initial condition, this you have to do, and in case of any doubt, you can discuss with me in the next class. Okay, so students, with this I conclude my transient response analysis using time domain approach for RL, RC and your RLC circuit. Okay, so thank you very much.